Hello, I'm Dr.S.David Jereil from the Department of Physics. Today I'm going to present a topic named Magnetostatics. Magnetostatics is the branch of electromagnetism that deals with the study of magnetic fields system where the currents producing them are steady or static. So what is magnetic field? Magnetic field is the region around the current carrying conductor where the force is exerted perpendicular to its velocity is called magnetic field. So it's a vector quantity, it has magnitude and direction. This was found by Oersted using Oersted experiment who unified electricity and magnetism. So there are some basic laws or rules. The one is Maxwell's screw rule. In that, if you ever see a right-handed screw is turned in the direction of the current, and the direction of the rotation is the direction of the magnetic field. So it is shown in the figure B that the right-handed screw it is rotated in the direction of current, and the direction of rotation is the direction of magnetic field. There is another rule called Maxwell clasp rule. In that, if you hold a hand like that, the thumb finger points in the direction of current, and the remaining fingers, as you can see in the figure A, shows in the direction of field. So there is another thing called Fleming left hand rule. So in Fleming left hand rule, so we can see in the figure like the thumb points in the direction of force and forefinger points in the direction of magnetic field, and I is the direction of current. They are perpendicular to each other. So what is magnetic induction? So magnetic induction is induction of magnetism in a body when it is placed in a magnetic field. So you can see this, if a positive charge Q, it moving at a velocity v through a magnetic field, it experiences force in the direction of F, then the magnetic induction B at the point as shown in this figure can be calculated using the formula F is equal to Q V cross B, which is nothing but F is equal to Q into dV sin theta. So from this you can derive the magnitude of magnetic induction. Magnetic induction B is F by Q V sin theta, where theta is the angle between P and V, and its SI unit is Weber per meter square or Tesla. So the magnetic induction is B is said to be 1 Tesla if the charge is 1 coulomb and force is 1 newtons and with a velocity of 1 meters s per minus 1 and theta is equal to 90 degree. So what is magnetic flux and what is magnetic flux density? So it represents the induction crossing through the surface S. You can see a surface, the number of induction magnetic lines of force passing through a particular area, it is called as magnetic induction. So it is given as pi is equal to integral of S B dot ds. Its unit is Weber. So if B is uniform, the magnetic induction is uniform, then A dot pi is equal to BA. Okay, if the magnetic induction B is uniform and normal to this area, it is A dot pi is equal to BA. So let us consider an area of 1 meter square. So if A is 1 meter square, pi is equal to B, the magnetic induction is numerically equal to the normal flux per unit area. Magnetic induction is equal to the flux per unit area, then therefore it is called as magnetic flux density. So then we go to the next one. What is magnetization? When a magnetic material is placed in a magnetic field, the elementary loops align itself in the parallel to the external field. The material gets magnetized and it acquires its own magnetic dipole moment. So here magnetization, it is called as magnetization, M is equal to magnetic dipole moment divided by volume. Okay. So SI unit is ampere per meter. So we will relate the relation between three magnetic vectors B, H and M. Consider a Roland ring. So you have seen the Roland ring. So Roland ring, this is another example, which is nothing but a toroidal winding of n number of turns. So if we have a toroidal ring with n number of turns, so as shown is in the figure, so a current is applied I naught through this ring. It gets magnetized. So the magnetization arises due to the alignment of elementary current loops. Okay, In the section 2, you can see that internal elementary current loops align itself to the external magnetic field. So this internal tiny electrons cancel each other due to the adjacent opposite directions. The numerous localized surface this form a localized surface current. They are replaced by one single current, that is closed surface current IS along the surface. This current is called as ambient current. So let E be the area of cross section. As I told you before, we are going to find the relation between three magnetic vectors B, H and M. B is the magnetic induction, H is the magnetic field strength or magnetic field intensity, and M is the magnetization. So in that Roland ring, let A be the area of cross section and L be the circumferential length of the ring, and L total volume of the ring will be L into A. So we already saw that the ring behaves like a large dipole magnetic moment, which is nothing but ISA. I told you IS is the surface current, ambient current, and from that we can calculate the magnetization. Magnetization M is the magnetic dipole moment per volume. So IS A by V. We know already the volume of ring, that is LA. So A get cancelled, we get IS by L. So this term is called as the surface current divided by per unit length is called as magnetization current. Okay, the surface current per unit length, which is known as magnetization current. So we know that magnetic induction B arises within the ring due to the free current I naught, which passes through the Roland ring, and magnetization of ring is due to the ambient current. Okay, one is free current and one is ambient current. So therefore B is given as mu naught into Ni naught L plus Is L. So here Ni naught L is the free current per unit length and Is by L is the surface current. We already know that Is by L is nothing but magnetization, which is M. So from that we can simplify mu naught NIL M, we take it into the conclusion, B is equal to mu naught Ni naught L plus M. So we can simplify B by U naught minus M is equal to Ni naught L. This term B by mu naught minus M is called as magnetizing field or magnetic field intensity H. So H is nothing but B minus mu naught minus M. So B is equal to mu naught H plus M. This is the relation. This equation 2 gives the relation between B comma H and M comma H points in the same direction of B or M. Its unit is ampere per meter. Okay. So H is nothing but Ni naught by L and is equal to nothing but Ni naught, where N is the number of turns per unit length, and the value of the magnetic material depends on the free current and it is independent of the core material. So when M is 0, in this term, when M is 0, the magnetic induction, there is no magnetic material in the core and there is vacuum in the core, then equation 2 becomes B is equal to mu naught H. In vacuum, magnetic field strength is related to the magnetic field induction by this equation. When the magnetic material is placed in an external magnetic field, it gets magnetized and occurs magnetic dipole moment. This procedure is additional magnetic, and here B is greater than B naught. In this such case, H is equal to B by mu naught minus M. Thank you.